So if we were talking about gases or liquids or solids, starting at the very technical basics would still be the right place to get started. But despite its being the most plentiful state of matter in the universe, even if that's not the case on Earth, since most people probably associate plasma either maybe with blood or sci-fi weaponry or something like this, we should probably begin with this. What is plasma? But more particularly, since you've answered this already in general, what are some plasmas maybe that we find on Earth?
Okay. Well, solid, liquid, and gas, are phases of matter. And we sometimes say that there are 3 phases of matter, but those of us who are plasma physicists say, no, that's not correct. There are 4 phases of matter. And as you raise the temperature, you go from solid to liquid to gas. And then if you raise the temperature high enough, then ionization of the atoms that are moving free and molecules that are moving freely in the gas takes place, and you reach the plasma state. That is reached when you get to a temperature of a few thousand degrees Celsius or degrees absolute, okay? And so beyond that, most, virtually all of matter tends to become ionized. When it is ionized, that means the electrons and the nuclei, or at least the ions, the partly neutralized nuclei, are charged particles. And charged particles are influenced, obviously, by electric and magnetic fields. They're pushed around by the fields, the electric and magnetic fields, and those fields become an essential part of the way that form of matter behaves. And as a result, it behaves quite differently in some respects from a solid or a liquid or a gas. It is a fluid, in the sense that it's not stationary in some kind of crystal lattice or material form, but nevertheless it behaves rather differently, and that's because the particles, when they move around, are influenced by the fields, but also they influence the fields. So magnetic fields can be generated by currents, as is rather familiar in lots of situations. So, for example, if we want to make a magnetic field, we can wind some wire into a coil, put current through it, and that'll generate a magnetic field. Similarly, the density or the number of particles per unit volume determines the electric field. So if we put a lot of negative charges in a place, a body that is negatively charged, has an electric field surrounding it, which will attract positive charges towards it. And so there's this interesting fundamental loop of consistency, which is that the plasma is affected by the electric and magnetic fields, but the electric and magnetic fields are affected by the plasma. And in the end, this system has to become self-consistent. And it's the fascination, or it's the exploration of that self-consistency, which is a big part of what we do in plasma physics. So maybe that's enough. You asked about applications. Perhaps your listeners are aware of the fact that they can hear me now basically because of things that are made using plasmas. Virtually all of the solid state devices, chips, and so forth that go into phones and computers and so forth are processed using plasmas interacting with semiconducting materials. And so perhaps the most widespread current terrestrial application of plasmas is to the manufacture of semiconductors, which is what makes our modern technological society possible. There are many other applications, but I would say the other extremely widespread importance of plasmas is in space. Space isn't just a vacuum. It has very, very low density once we get outside of the atmosphere. But actually, the particles in space are mostly ionized. In other words, what is out there in space beyond the Earth's atmosphere is plasma. And in fact, the plasma surrounding the Earth is responsible for all kinds of natural phenomena. So people might be familiar with the aurora borealis, for example, which is the northern lights. Those northern lights are caused by the precipitation of plasma electrons from the surrounding magnetic fields of the Earth into the atmosphere. And so they're a sign of the influence of plasma on our lives. Now, that might seem a pretty distant influence, if you don't live in Alaska or somewhere. But actually, for modern communications, for satellites and things like this, the influence of the plasma around the Earth can be very important. The plasma around the Earth, actually, by the way, is the reason why we can, with wireless, transmit short waves all the way around the Earth, because actually radio waves propagate in straight lines. And so if you had, on the surface of the Earth somewhere, a transmitter, and there were no plasma around the Earth, the signal from that transmitter would just go out in one, half plane, and there would be no way for someone in North America to have radio contact with someone in Australia. But in fact, starting in the early 20th century, people were able to talk to one another around the world because there's a plasma around the Earth that reflects the radio waves back, and they bounce around inside that plasma and can therefore make it from North America to Australia or anywhere else on the globe. So there are a few examples of how important plasmas are to our lives and to our understanding of the world.
Okay, well, you described plasma as a fluid because it's not stationary, but is it fair to say that plasma is closest in similarity to gases? And hopefully you don't think this is silly, but the reason that I ask this, though, is I want listeners to be able to understand on a more visceral level that they might associate with touch or sight, just what plasma is like. And maybe it's impossible to answer this because so much varies on density and temperature. And I mean, you can't touch the sun, for instance, but maybe you do have an answer to this.
Well, actually, although this is a little old-fashioned, fluorescent lights are a very familiar example of a plasma that we used to have in almost all of our rooms in shops and in our homes even. Of course, we're gradually replacing those with semiconductor lighting systems now because they're a bit more efficient. But basically, that's a very cold plasma by my standards. It's the temperature inside that fluorescent tube, let's for example, is essentially it's a gas. It's a rather low density gas. It's a density that is typically much lower, actually, than the air in our rooms. So it's a very tenuous gas, but it is a gas. And what's happening in a fluorescent tube is that the gas in there is being ionized. It's carrying, as a result, being able to carry an electric current, and that electric current heats the gas and causes the neutral particles that are left behind. Not all of the particles are ionized to emit light. So yes, a plasma is a gaseous medium, no question about it. We have a distribution of particles that's moving in random ways with a random set of velocities and directions. But the key difference between that and a neutral gas is this influence and mutual influence with electric and magnetic fields.
Well, this, since you mentioned the low density of fluorescent light plasma, the plasma that's in there, this I just found very interesting that I learned recently. So I have on my desktop is a famous image of the pillars of creation, which you'll be familiar with. And so this nebula, is it plasma? I know it's gas. I'm not sure if it's. I know some nebulae are plasma, but
Broadly speaking, yes, it is a plasma in the sense that it is a gas that is largely influenced and controlled by electric and magnetic fields. Actually, in astrophysical plasmas, gravity is also extremely important because of the very large scale of those plasmas. On Earth, gravity is not important for most plasmas because they're smaller and the gravitational force is therefore much smaller than the electric and magnetic forces. So the answer is yes, it's a plasma. Those of us who are plasma physicists are sometimes a little peeved with our astrophysical colleagues for always calling gaseous media in space gases. For a long time, they've had a headache using the word plasma, and I understand that because it's not so familiar a word as gas for the person in the street. But the fact of the matter is, they are exactly what we call plasmas. In the case of nebulae, though, there are usually other constituents in the plasma. There is dust, and that's usually very, very important in a nebula in a way that it isn't so important, for example, in a star or let's say in most of the space weather that's going on around the Earth. So it's not a pure plasma. It's got other stuff in it.
Mm-hmm. Well, I actually wanted to get to that dust in a moment, but what I was going to say is, and the reason that this came to my mind based on your mention of the low density plasma in a fluorescent light, is that when you look at these images of the pillars of creation, like I have here, for lack of a better word, these clouds, they look almost tangible. They're so concrete. But what I learned the other day is they are far, far more rarefied even than the air around us by many, many orders of magnitude. They are so not dense. And I just found that fascinating.
To give a specific comparison, if you were to think about a cubic centimeter, so a little box about that big, okay, the plasmas in space around the Earth, the so-called space plasmas, typically have densities of particles that are a few particles per cc, per cubic centimeter. Okay, so that little box would have a few particles in it. The densities in astrophysical and galactic space can be even much lower than that. Okay. That's to compare with how many particles are there in a normal gas in that space. Well, it's probably 10 to the 20th or it's many, many orders of magnitude larger. So there's an enormous difference in density, and the plasmas that I deal with, even on Earth, tend to be much more tenuous than the density of the air at atmospheric pressure around us. There are some plasmas that people are interested in and study that are in atmospheric plasmas. There are some naturally occurring ones, such as the aurora, such as lightning strikes, and so forth like that. And there are also some technological applications of atmospheric pressure plasmas, but usually the density of the charged particles in those is much less than the density of the uncharged particles. So we are often dealing with impure plasmas.